So let's talk about RSA. RSA is the original public key cryptography system that changed the world. We've all been using it since the 70s. So the way it works is this. You have a public key and a private key. And so first you choose two large primes. These are secret, P and Q. Then you multiply them together, and that's the main part of the public key, N. The other part, E, you just choose a common number, like 3 or 65, 537. There's a couple of common numbers you use there. It doesn't matter much what you use for E, and these are not secret. You publish, the public key is this number N and E, and N is the product of two prime numbers. And you then, that public exponent here, there are certain rules for it, but like I say, 3 and 65, 537 both work, and I've never seen anybody use anything else. I see someone asking a tip for the second part of the hash extension project. Well, there's still one thing you don't know that you'll have to guess by brute force down there, that's all. You don't know the length of the secret. You'll have to keep trying lengths until you find one that works. Anyway, so that's the game. Then you compute this thing called phi. You could, but that's the point. So we're just going to do this. We're going to use P equals 7 and Q equals 23. And prime numbers this small are not secure at all, of course. Anybody could find them by brute force, but you'll get to see how the process works. This math is the same, except you'll need longer keys to make it secure. So we'll set P is 7, Q is 23, and calculate N from them. That's the first thing. So there's the public key. P, Q, and N. N is 161. All right. Now we calculate phi of N, which is this quantity called Euler's totient, I think. P minus 1 times Q minus 1. It's pretty important in the math of RSA, but it's where you're going to use it as part of finding out the decryption key. So this is the N, the public key, and this is Euler's totient, 132. Now we choose E equals 5, that'll work. And now this is the hard part, we have to compute private key. And if you remember the modular arithmetic, am I using Python 2.7? Why, George, I am. Well, that's strange. Now that you mention it, yeah, let me get out of here and use Python 3. Of course, you can do it in Python 2.7, but something bad will probably happen if I keep doing that. Python 3, oh, I've got it. Thank you for telling me. Good. I wondered, that's why it's printing the parentheses around things when I print them. Okay, good, thank you. I forgot that Macs still have Python 2.7. They shouldn't. Python 2 has been deprecated. But anyway, all right, good, thank you for telling me. So now, remember we talked about this before. You're doing math on a ring. You're doing math mod n. And in this case, what matters is phi. What you need is you're going to encrypt with a key of 5. The reason you choose a small number for E is so encryption is a fast operation. And if you make encryption a fast operation, decryption is a slow operation. And the way this is normally used is the keys on a server, like Google, and the client machine is something weaker, like your browser. So you want your browser to have an easy job, and it's okay if the server has the hard job. So the encryption, which you do to send your data to Google, is made fast by choosing a small number for E. The decryption key is hard to find and much larger, which slows things down. So what you're going to do is take your message to the power E to encrypt it, and you're going to decrypt by taking that to the power D afterwards. So you have to find a decryption key which will undo the effect of the encryption. So we need to find, this is what we need. We need a situation where D times E mod phi is 1. That's the condition which will cause the decryption to undo the encryption. So there are some sophisticated algorithms to make this faster, but we're going to find it just by brute force. So if E is 5, and you print 20 times E, you get 100, of course. So we're just going to find what, now we're going to do these multiplications, modulus phi, and we're going to see how it goes. So we're going to do a series of these. We're going to count up by 5s. We're finding multiples of 5 there. And so this is 100, this is 130. Here's 131, is 131. Mod percent fin. Phi is 132, good, thank you. I thought it was 131, it's 132, that's right. It's always going to be an even number because these are two even numbers, good. And so when you go one more, 132 is going to give you 0. So we've gone around just to see how this works. So now we're going to find all the multiples of E. We're going to try a bunch of multiples and see if we can find the one that gives us an answer of 1. And what happens is for 100, 105, 110, 115, 120, 130, and the next one wraps past and gets us to 3. So we missed 1. So we went all the way around this circle, but we missed 1. So we have to go around again and try to hit again until we find the number that will give us 1. So this was about 26 it took to go around. So it's going to be up around 52 is the next time it passes. So let's try some numbers up near 52 and see if we hit 1 this time. And see, now we do. 53 gets you 1. So the encryption key is 5 and the decryption key is 53. And that will undo the effect of the encryption key. So now we can encrypt a message. And here's how it works. Your public key is N and E. And Megan has calculated that from her secrets, and these are the numbers we've used. The decryption 3 is 35, and that's the main thing she needs. P and Q, the decryption key, is mainly what she's going to need. So Q-Ball wants to send this message. Now you have to turn it into numbers. So what I'm going to do is encode it with ASCII, each character one by one, and I'm going to encrypt each number one by one, which is not the simplest or easiest way to do it. It's just, you don't have to think. So now the way you encrypt things is you take the input number, X is the plain text, you take it to the E mod N, and you send that. That's why this is so popular. It's pretty simple. So that means 72 to the E mod N, 105 to the E mod N, 33 to the E mod N. This is the encryption process. Okay, so 72, 105, 33 turns into 151, 119, 157. That's the encrypted message. Now to decrypt the message, she takes that ciphertext to the D. And as we just went through, D is the power that will undo the E. So she takes these numbers, 151, 119, 157, to the D. And D is 53. And that gives her the original numbers, 72, 105, 33. And those are the ASCII for HI exclamation point. So that's encryption and decryption. That's all you have to do is those steps. So there's just a series of flags here. That's it. Find a couple of flags, and you get to practice performing RSA encryption and decryption for very small values. So you get to see how it works. And of course, all you do for making a finished cryptographic system is you use much longer keys, and you consider encoding the message in a more smart way than just using the numerical values of the ASCII characters one by one, and padding and things like that. All right, so that's what I wanted to show you.